Okay, hi everyone. Welcome back to the Topos Colloquium. Today we are very pleased and honored to have Leonardo de Moura, and he's going to be talking to us about Lean 4, empowering the formal mathematics revolution and beyond. Leonardo, whenever you're ready. Thank you so much.
Oh, thank you very much for the introduction, for the invitation to be here. Super excited to tell you about Lean and the Lean as a whole. Lean is a proof of systems and a programming language. Lean is based on dependence type theory. We built Lean with these four goals in mind. We wanted to have extensible system, like it's not just extensible proof of systems, but also extensible programming language. It should be expressive. I think we covered that by having dependence type theory as a foundation. But we also want scalability and efficiency, right? You're going to see later how important these two aspects are for the Lean community, for our user base. We see Lean as a platform for doing formalized mathematics, software development, and verification. We are also excited about this third bullet, right? Developing custom automation and domain-specific languages. People familiar with Haskell will love Lean as a programming language. There's a lot of inspiration. Haskell was a main source of inspiration for us. Haskell has been very popular for defining domain-specific languages, but when you use Lean, you get the extra advantage that you can use it not just to develop your domain-specific language, implement it, but also reason about it, prove properties about your domain-specific language. Lean has a small trusted kernel, right? And we have many external type and proof checkers, right? Many people view Lean as a development environment for formal mathematics, right? Proofs and definitions are machine checkable. The Lean math community is growing rapidly. They love the system, right? I would never predicted that it would get so popular in the math community. When we were at the beginning of Lean, we had Jeremy Avigad was our first user. We were talking, we dreamed to have an impact in mathematics and software verification, but we could never predict what would happen later, right? And Jeremy summarizes really well the project. He says, well, this is a work of love for everybody in the project, from the Mathlib community, the developers, people that are joining there for whole. They're extremely passionate about the project. You can also view Lean as a compiler for mathematics if you're a computer science person, right? You have this high-level language, and there is a process that we call elaboration that converts this high-level language into kernel codes, right? The codes that you can view like a very low-level codes that the kernel checks, right? And here I have a small example of actual Lean code, just to give you an idea that we have, it's similar to a programming language. We have all these extensions that allow you to use your favorite editor. You can use VI, you can use Emacs, and VS Code that right now is the most popular editor used by popular, I mean, in the Lean community, but also popular in other programming languages. And we have all the goodies you'd find in a system like that. You have auto completion. You can hover over things and then you give back information. It feels like as a digital assistant when you're using this kind of interface. Lean is also easy to install. I mean, if you have VS Code, it's very easy. You just need to install the Lean extension, Lean 4, and boom, everything's working, right? And if you don't have VS Code, I suggest you install it, and you're going to be able to play with Lean in no time. But we keep trying to make it better and better, make the usability better, right? One you're going to find in this talk, one common theme is like the amount of effort we're putting to make things convenient for users, right? This is so important, and many times overlooked the importance of having good engineering, good usability, scalability, and so on. We claim that Lean enables a form of decentralized collaboration, right? Many people in the past believed, oh, Lean has a big team. No. There was only one person at Microsoft, it was just me at Microsoft, and bunch of volunteers all over the place, right? Many people contribute to Lean, to its mathematical library, but it's completely decentralized efforts, right? We never had a team. With the FRO now, is the first time we're building a team dedicated to the project. But how this form of collaboration happens, right? The first thing, Lean has a strong metaprogramming system, right? People can extend Lean using Lean itself, right? They can not use Lean just to write their proofs, but they can also write their own proof automation. They can write their own visualization tools. They can write their own notation without even talking to the developers, right? They can do that independently. They can push the system, customize the system to their needs. And they may think like, oh, a mathematician would never do that. Actually, it's not true. In Mathlib has more than 1 million lines of codes, but it has 40,000 lines of extensions, right? And yesterday I counted the number of people that contributed these extensions. It's like 10%. I mean, they have 300 contributors, but 10% contributed meta programs to Mathlib. The other ingredient is formal proofs, right? Formal proofs are great because they are machine checkable. You don't need to trust me to use my proofs. You don't need to trust my proof automation to use it, right? Everything's creating these formal proofs that can be checked by the kernel. And I feel maybe it's redundant to tell you that most of you know that, is that it's powerful. It allows you to hack without fear of introducing unsoundness, right? You can add a new form of proof automation that you may not be fully sure it's correct, but you know in the end, a formal proof is being generated and it will be checked by the Lean kernel. This gives you don't have to fear, you can extend the system with confidence that you will not introduce unsoundness. Here I have a small example showing how we model things in Lean. Lean has a concept of classes like Haskell, and you have inheritance. Here is saying, oh, we have a type, you say the type alpha has distributivity property. If it has addition and multiplication, and these two properties hold, right, the left and right distributivity. Then you can use this concept to define a ring. A type alpha forms a ring if it's an additive commutative group, it's a monoid, and has distributivity property. After you do that, let's see another example. You define a matrix. This is a very high level definition of a matrix is, right? They don't even specify what M, N, R. It can be anything, right? Any type M and N. After you define it, you have this very general definition for matrices. You can define notation for manipulating them. You can show how you add addition behaves for matrices. And you can see here the notation is very compact. Then you can prove, for example, we have this class ring. You can say that a square matrix form a ring, right? If there are some conditions here, and here should be a finite type, it should have decidable equality. There are all these details that I'm not going to go to describe all of them, but just to give you a flavor of how the language looks like. And finally, you can prove theorems. I mean, this example, I'm using the notation. You see the addition is being used here. You have transpose this superscript for the transpose of a matrix. We have metadata here, like this at square bracket simp is a metadata notation, right? You're saying that you're telling Lean you can use this theorem as a rewriting rule, as a simplification rule when you're proving theorems. Here's very high level, just to give you a flavor on how Lean code looks like. A question we get all the time is, should we trust Lean? Also, software has bugs. How do we know a proof we constructed using Lean is correct? Like the Mathlib has more than 1 million lines. Probably there are bugs there. Well, we say, okay, Lean is a big system, right? There are many extensions, and probably Lean, the extensions, they all have bugs, right? But it doesn't matter. What it matters is that we are only relying on this small trusted checker, right? That is in the kernel, right? It's much smaller piece of code. But then someone can say, well, it's small, but it probably has bugs too. Okay, yes, maybe it has bugs. A lot of people inspected this code. But yes, I will not dispute that may still have bugs. But then you can export the proofs. Recall that Lean has been implemented in Lean. All the internal data structures are available to you. You can write Lean codes, manipulate that traverse the environment, traverse all proofs, all definitions, and you can export them to using your favorite formats. You can manipulate them, you can visualize them, you can do whatever we want. They are all first-class citizens. And people have implemented checkers in Haskell, Scala, Rust, and so on. And you can implement your own checker if you want. Usually people that are familiar with functional programming or they have some idea on how dependency type theory works, they usually implement in 1 week their own checker. I've seen people that's implemented in 1 day, but of course, with people that are very familiar with dependency type theory. But the point I'm trying to make here is that it's not a gigantic task to implement one of these external checkers. And the Lean community develops Mathlib, the Lean mathematical library. Here I'm showing just the maintainers. I mean, now it's, I should update these slides. We have more organization. There are administrators, maintainers, community organizers, people that ensure the community behaves in a peaceful way. They blow me away all the time. I mean, in 2017, when they told me they would do that, I thought they were going to fail. Something like Mathlib is like a software library. I strongly believe you need discipline to build software. I mean, when I look for in a collaborator, the most important thing is whether this person has discipline. I mean, this is really important. And I thought mathematicians would not have the discipline. I mean, sometimes developing software is fun, but it's also painful. There's a lot of, you have to refactor code. This is usually not fun. And I was assuming, wow, they're not going to do that. I thought they were going to fail, but they succeeded. They proved me wrong. And some of the mathematicians are amazing engineers. Maybe they don't know, but they are. I mean, they're really amazing engineers. I will tell you more about that. And they published this paper. There are so many, it was infeasible to list everybody in this way. The paper is authored as the Mathlib community, and it's amazing to see this community growing. And here I have a graph with some statistics. It feels like it's stabilizing the growth is because in the last few months, the whole community has been porting the Lean library, the Mathlib to Lean 4, right? In this way, they froze the current library until the port was complete and was completed last month. But even with this freeze, right now there are more than 100,000 theorems, more than 300 contributors in Mathlib, right? 66,000 definitions are there. And it's the basis of much more ambitious projects. One of them, one that actually attracted many new people to the community was the Lean Perfectoid spaces, right? Perfectoid spaces were popular because Peter Schulze got a Fields Medal, right, in 2018, and everybody wants to understand what a Perfectoid spaces is. And one of the very popular question answers at Math Overflow is a link to the developments in Lean, defining what a perfectoid space is. For example, for me, I would never try to understand what it is, but now I can understand, at least I can follow. For example, it uses state ring. I don't know what a state ring is, but I can click and jump to the definition and learn about it, right? It's an interactive object that you can manipulate, you can visualize, you can keep following the definitions until you get to something you actually understand. I mean, it helps you to understand what's going on. And I think it is a powerful idea, right? It's a powerful use of a proof assistance. It's a way to communicate. The graph we have here was automatically generated, right, for the project, showing the dependencies, right? That's another thing. After you have a formal representation of a mathematical concept, it is data. You can manipulate, you can create visualizations automatically, right? And I think this is another thing that's extremely powerful. I will tell you, I will tell you about the Lean ecosystem now. We have, of course, the developers, I mean, GSATs, right? But there are different groups. I mean, if you start hanging out with the Lean community, you're going to see there are many mathematicians there. They work on Mathlib. There are many projects like the liquid tensor. I will tell you more about it in a few slides. We had the formal abstracts, fly pitch, and so on. Right. Another big groups, people that are building AI for mathematics, right? In the past, we had OpenAI, built this GPTF for Lean. We have Facebook AI, also, well, now it's called Meta AI, but they also built an assistant for Lean, and it's integrated with the Visual Studio Code interface there, right? And it's growing. We have new, I will give more examples of groups that are developing AI for Lean. And we want to support them, especially in the FRO. Now, it's great the FRO is a non-profit, so we can serve all these groups without concerns about one competing against the other. Before, for example, when Meta was developing their assistant, when they released a blog post about it, they made a huge effort to not mention Microsoft anywhere, right? I fully understand this kind of concern, but now it's gone. I mean, all the developments centralized in a non-profit, right? And avoids, and that's in the non-profits, we want to contribute and collaborate with everybody, right? Anybody that wants to develop systems on top of Lean, we are there to support this effort. Software developers, right? We believe Lean is also a great programming language. It's our favorite programming language, right? Sometimes we say it's a language where you program your proofs and prove your programs, right? And it's fun. I mean, we have examples like at Galois, they implemented this controller. They wrote a piece of code that controls a robot using Lean codes, and they have a blog post about it. I invite you all to if you type in Google Galois robots Lean, you're going to find this demo where they have a video showing the robots working. It's really fun. Students, right? We also believe you can reach self-motivated students. Before, I didn't have the self-motivated, but a friend of mine that's into math education told me, come on. I mean, math education is way more complicated than that. I said, okay, let's use only for self-motivated students, right? There are a lot of people that learn to program by themselves without any guidance, right? Because I believe that there are lots of information available online, and they have a playground, a compiler, an interpreter where they can play with. And I believe proof assistants provide the same kind of playground for mathematics, right? I remember when I was a kid, it wasn't clear to me what a proof is. You go around asking people, is this a valid argument? People would say, no, you don't really, the rules are not clear. You keep trying to learn. Without a mentor, it's really hard. But with a proof assistant, you have the computer there telling you if you're making a mistake or not, right? And I believe you can reach one dream we had is like, it would be awesome. Like imagine 20 years from now, we have a Fields medalist that's tell the whole world they learned mathematics using a proof assistant, right? It would be amazing, right? The Lean Zulip channel. If you want to learn more about Lean, go there. It's mind blowing the amount of messages you find there, right? That thousands and thousands. I can't read everything. I wish I had infinite time in I could read every single message, but it's not feasible anymore. But you'll find there people like Peter Schulze. He wrote so many, it's insane. I mean, the number of messages he wrote there explaining history to the community. You find people that are experts in machine learning trying to connect their systems to Lean. You find people celebrating new results, or people asking questions, right? We have a new members channel stream there where people can ask very basic questions. Yeah, I have a blast with the Zulip community, and if you have a question about Lean, they answer in minutes. I mean, it's super fast. I mean, it's better than any form of documentation. Of course, it's not scalable. We are trying to work on better and better documentation, but it's great to see it in action, the community in action. In 2020, I think was the year where Lean starts getting really big, very popular, right? We had this article in the Wired magazine, Quanta uh, uh, selected Lean as one of the math and computer science breakthroughs. In this article that showed up in Wired and Quanta, wow, it had a huge impact on me. Because it was like I could see the impacts the community was making, the difference, the idea that we were trying to build something that would be the foundation for other people to build on top of. There's so many great quotes, and I use it as inspiration to work on the projects. In 2021, the liquid tensor experiment started, right? Peter Schulze had these results he wasn't sure about. People were using his lecture notes, but nobody was checking whether his proof was correct or not. And he wasn't sure, and he posed this challenge, right? I remember when Kevin Buzzard contacted me, telling me, "Oh, we're going to go for it." I said, "Oh, wow! I mean, are you sure it can be done?" I said, I don't know. Maybe it's going to take 3 years to do it." Right? I said, okay, we're going to do anyway. I mean, even if it takes 3 years, we're going to do it. But to my surprise, I think to everybody's surprise, they finished in a couple of months. The main part that it took a long time, the whole thing, less than 1 year for sure. But the main thing that the main result Schulze was unsure about, they proved very quickly, right? And it was mind blowing. Showed up in Nature News. Peter Schulze, I think he was impressed based on these quotes he had, saying that the result was really complicated. It was like a thick jungle to navigate. I think everybody was surprised. And the other surprise that the Lean community managed to simplify his proof, right? He was using these gadgets, the bring the line complex, and people noticed that it was overkill. You didn't need it, right? And they managed to simplify the proof. And Johan, that was one of the leaders of these efforts, told me he could only see 2 steps ahead. right? The computer was there assisting him. Imagine trying to simplify a proof that you can only see 2 steps ahead. This was only possible because they had computer guidance, right? The computer was helping them navigate this thick jungle, right? And I found this mind-blowing, right? First, you had this team of people that collaborated to achieve these results. Some of them never met in person, and they managed to simplify a proof of a result of this caliber, right? So, I mean, for me, it was wow, was unbelievable. I mean, it was one of the happiest days when I read these quotes. 2023 has been great for Lean. I mean, we're excited for so many different reasons, right? We had this event at UCLA, and Tensor was tweeting about, well, was Mastodon at this point, but he was texting about, I don't know how you call people using Mastodon, but it's this open source replacement for Twitter. But we're super happy to see his engagement of Tensor. He's one of the greatest living mathematicians today. We had the article in New York Times mentioning Lean. We had now a new article in Quanta mentioning Lean again. We're so happy about this the support we received. And we finished, the community finished porting Lean. Was another thing, I had so many doubts this would be feasible, right? When we started Lean 4, Mathlib was so tiny, right? And we felt, in the worst case, we port by hands. I mean, so tiny, right? We will do it. We never expected that while Sebastian Ulrich and I would be working on Lean 4, Mathlib would grow from a few thousand lines to more than 1 million, right? We never expected that. We thought, okay, in the worst case, you're going to port this stuff by hand. It's no big deal. But then when Lean 4 matured, we had 1 million lines. I said, how do you port that? Everybody kept telling me this is impossible. This is impossible. You're going to fail. It's going to be like Python 3 and Python 2. The library will never be ported. The community is not going to be able to do it. I felt I was feeling it would not happen. I thought it was going to fail many times. But to my surprise, they succeeded again, right? It's a community. There's so many heroes, people that came from nowhere to help. And another big news that was completely unexpected, Daniel Bernstein, he's a cryptographer, and he did from nowhere, he did these big developments in Lean, right? Using Lean to verify these GOPA codes, completely unexpected. And he uses results from Mathlib. This is a proof that having a mathematical library, how important it is, right? It's the foundation for so many projects. Another talk I really invite, I think you should all, this talk is available online. It's by Johan Kommelin. He's one of the leaders of this liquid tensor experiments. He describes how he approaches the liquid tensor experiments, right? He defining abstraction boundaries is the same ideas we have in computer science for organizing a project, making sure that people can collaborate. After you define the interfaces, people can start working concurrently. It's a beautiful talk with many great insights. I invite you all to watch this talk that's available online. It's a great talk, great title, Abstract Formalities. And I told you about extensibility. Now I want to tell you a little bit more, right? That we're building Lean not with the community, not for them, right? I mean, they help. I mean, the community adds so many extensions to Lean. And some of these extensions, sometimes you're not even aware they exist. We learn later, right? And this is super powerful. For example, the ring tactic, the community implemented. Mario Carneiro implemented this ring tactic. There was another student, I'm sorry, I forgot his name, that's implemented another version. Then Mario ported it to Lean 4, and it's there. And he extends, other people contributed to this tactic, and it's a piece of proof automation that's there and it's heavily used by the community, right? And because you have all these extensions in Lean, written in Lean itself, it's important that Lean is also efficient programming language, right? And this was one of the main limitations we had in Lean 3. Everything was interpreted. Now everything is compiled. We're putting a lot of energy in making sure that it's super convenient. People don't even know what a compiler is, what a shared library that's dynamically created and then in linkage with Lean. They don't need to understand that. It is all transparent. And this is really important. Making things convenient for the users is super important. And there are many extensions, many new ideas have been added to Lean. Sebastian and I started, then Dan Lyon worked with us to extend the ideas. One fun fact is that the Lean Memory Manager, right, that's Dan Lyon designed, now is part of the Bing Memory Manager, right? It's actually used in Bing, and then when there, it reduced the latency of the, and he was telling me, I think now, even ChatGPT now is faster because of this memory manager. And then design the memory manager for Lean, was not for Bing. It turned out that it was great for Bing, it was great for ChatGPT. And we think there are many other ideas that will come, right? Using proofs to optimize the code, right? Having a proof assistant as your programming language opens so many new possibilities. And we support domain-specific languages. I'm going to give many examples. And this is great. I mean, one idea we have, like, I love this saying Sebastian had, it's like, we need a hygienic macro system because simple things should be simple, right? I mean, if the user wants to write a simple new notation, right, for formalizing some piece of mathematics, this should not be rocket science, right? It should be simple, right? And this is a motto that we keep using over and over again. Simple things should be simple, and we want to allow users to define their own little languages inside of Lean, or even big ones. And we use these ideas ourselves. For example, Lean supports monadic code like Haskell, but on top of that, because we had this extensible notation, extensible syntax that allow us to define our own notation, we use it to implement Lean ourselves, right? For example, we have notation for writing for loops, but this for loop behind the scenes is just a fold that we have in languages like Haskell or Camel and so on. But the nice thing that is super convenient, I love folds, but I always get confused or the order of the arguments, which one is the accumulator, which one, with a for loop is so easy. There's so many idioms that you capture with a single notation, right? And the users love these extensions, right? It feels like you're writing imperative code, but it's just functional code in disguise, right? And it's super popular with the community, these extensions. And even I showed here in the previous slides a tiny example for evaluating a polynomial, but you have, you have big pieces of automation like building congruence proofs, right? This is actual Lean code. This is the actual implementation using the same notation, right? This not extensible syntax where you define this for loops, all these extensions being used here to write a piece of automation in Lean itself. The static framework in Lean is also implemented the same framework, right? You view the static notation as a domain-specific language for constructing proofs interactively. Again, the users can extend it, they can add their own new primitives. They don't need to contact us, they can create their own fancy notation, and they do all the time, right? And they don't, in the past, they would have to keep asking us, please, could you do it? Now they don't have to ask permission, they can just do it, right? And this is powerful, right? It enables this form of decentralized collaboration that I was telling you before, right? This is actual Lean proof, right, that we got from our main repository is using the static notation. And in the Mathlib, you find many, literally millions of lines of code written using this approach, using this DSL. And you can add new primitives in Lean. For example, we have the case static for doing case analysis. Here's the implementation in Lean. But for example, power users like Mario Carneiro, he implemented his own version he calls R-Cases that has millions of bells and whistles, right? And a lot of people love his bells and whistles, and they are using these bells and whistles, and we are super happy they are doing it, right? This way, we provide our bare bone case analysis static, but the community can implement their own version that's more powerful, that's great for some specific domain of mathematics. There are many challenges, right, in Lean, right? I'm telling you all the success stories, how we got here, but we have many challenges ahead of us, right? Automation is one of them, right? I mean, many mathematicians don't want to spend time proving trivial things. We want these gaps to be filled automatically. Today, the overhead factor, for example, for the liquid tensor, people estimated on 20x, right? When you compare the informal proof with the formal one, they estimate a 20x overhead for the formal one. The goal is to get this to 1, right? It would be amazing. But the challenge is dependent type theory is a rich foundation, but it's also very hard to automate. The community has a lot of experience, I mean, in automated to improving from first order logic, right? But so far has been very challenging to lift these techniques from first order to dependence type theory. Many people succeeded, especially with Isabel, to lift this kind of automation to higher order logic, but for dependency type theory is still a challenge, right? We have many attempts in Lean, in Coq to do these lifts, but in practice, they are not very effective so far, but we are going to keep trying new ideas. There are people joining the Lean FRO to work on this problem, and we hope we are going to make we'll have a big impact in this area in the next following years. Another problem is scalability, right? Mathlib is growing, right? In the beginning, people were telling me it was way more dynamic, right? Because it's growing, it's small. When you submit a contribution, it can be quickly tested. You can get feedback very quickly. And this is very exciting, right? You get feedback, instantaneous feedback. Now the pull request queue is the contribution queue, right? That many people sending contributions, it's huge, right? There are so many. And to test each one of them takes time, right? And so you want to scale just to distribute, I mean, the pre-compiled binaries for the library is a challenge, right? You have scalability all over the place. The data structures used to implement Lean we have to make them more scalable. The engineering efforts, the code generator should be better. Everything should be faster. Everything should be better, right? We want to be able to process a mathematical library with hundreds of millions of lines of code, right? We will have to innovate in this area to be able to accomplish that. Usability is another big deal, right? I mean, we made a lot of progress with contributions from KIT, CMU. When we were at Microsoft, I was in Microsoft, we had hundreds of commits from people from all these places contributing to the user interface for Lean, to the language server protocol. Like, I mean, the part of Lean that's sending information to the graphical user interface. For example, when you hover over some objects, you get information back. There's a server that's providing this information. Feature like auto-completion, jump to definition, all these features, this was a big joint work. I mean, people at CMU, KIT, Microsoft, all over the place, helping to make this a reality, right? And again, yeah, it was funny that when we were doing that, many people thought, wow, it's not going to be possible. I mean, so much work. Maybe Lean 4 will not succeed because we don't have resources for building all this infrastructure. But again, the community proved that it's possible, right? People that many of them never met in person managed to make this happen. And now we keep like one big deal in proof assistance. It's not when the proof works, but what do you do when the proof does not work, right? Trying to understand why a proof doesn't work. At one point in Lean 3, we had traces, right? But traces were just a bunch of strings, right? We could grep, but grep is such a low-tech technology to understand why you have this huge file with a bunch of trace messages. You have to look manually. Oh, maybe you can use grep, but whoa, it's horrible experience. In Lean 4, traces are first-class citizens. They are data structures. And because they're data structures, you can write Lean code to visualize them. And actually, we have that now. Gabriel Ebner worked on this infrastructure. Now you have in notes, like if there's a problem, there's like a bomb or a red tick saying this is problematic, you should pay attention here, right? And this is super valuable, right? These trace messages. And we're going to put a lot of efforts in the next following months, making sure the traces are better, right? Are more informative, contain more information. And this is super helpful. People spend a lot of time trying to understand why something did not work. And now, another cool feature that was developed mostly at CMU, but with contribution from many different people. Ed Ayers, I think he was not at CMU anymore when he contributed. He was also a key contributor of this feature. Wojtek Wojtek is a former intern of mine, but he's a PhD student at CMU, and he built with Ed this amazing infrastructure. It's like you can write in Lean your visualization. I don't have here the full example, but the code to create this visualization is in the same file where the commutative diagram, the mathematical concept is defined. This is very powerful, right? You can define in Lean your visualization, have it there, right? Helping you to understand the logical context, right? The proof context of the proof you're trying to do or the code you're trying to implement. Another challenge is the language, right? How formal mathematics, a common question we get, how formal mathematics should look like? We don't know, we are learning, right? I mean, Lean, we can tell you that Lean is a rich and extensible language. We have many concepts there. We're always listening to the community, right? There's no spec that tells you this is what you have to implement. You are learning as you go, right? I mean, you don't know where you're going, right? There's no spec, and this is one of the main challenges here. I like to say that Lean enables AI for mathematics. I told you before about this OpenAI GPTF system, and they managed to solve some Math Olympiad problems using Lean, right? If you search for OpenAI Math IMO, you're going to find their blog posts and their paper with examples. Very interesting work. There's also the one from Meta AI, this hypertree proof search, right? You see that's integrated with the Lean interface. Unfortunately, this is for Lean 3. I hope they're going to port everything to Lean 4. There's also Lean Chats, that's auto formalization tool by Zangier and Ed Ayers. The same guy that was working on these visualizations. He also worked with Zangier on this auto formalization tool for Lean. It's really cool. You can start writing in English, and you interact with these bots. And it gives you back the formalization, and you can keep telling, no, I think you made a mistake here. And it's like an interactive process, right? And there is also Lean aids by some former colleagues of mine and some people in the Indian, it's not the Institute of Technology, but I think the Academy of Sciences, Indian Academy of Sciences. I'm sorry if I'm mistaken, but Siddharth is there. And they implemented this auto formalization tool. This one is for Lean 4. You can also for Lean 4. You can write in English in a comment, and you convert into formal Lean formulas for you automatically. It also is powered by large language models. This Lean Dojo now is by Caltech with collaborators in many different places. Some of them are at NVIDIA, but this is an open source framework for doing machine learning for Lean. I think I met with them a few weeks ago. I'm super excited about their project. It's got a lot of traction. Yeah, I want to see this. I mean, they care also about having models that are small enough that can be ran on your own machine. I think this is super important to disseminate this technology. But I always like to point out large language models are super popular now, but I also keep I keep reminding people that automated improving technology based on SAT, SMT, first order tier improvers like Vampire, E, and so on, superposition, are also extremely powerful, right? For example, there are these results by Mariano Hoyle. It's really influential. I don't know if you have seen. I mean, he found counterexamples for open conjectures, prove open conjectures, all using set solvers, right? And it's bringing a lot of attention, like it's showing mathematicians that this technology can help them proving new results or disproving important open conjectures. And I dream in the day that we can link and be the gateway. You can do your mathematical modeling in Lean, but you also have access to this kind of infrastructure in the background to allow you to explore these conjectures. I'm getting to the end, but one thing I like to emphasize, yes, there's a lot of engineering in Lean, right? I mean, I would love to tell you that we only work on theoretical results, new algorithms and data structures. Yes, this is not true. There's a lot of engineering going on. There's a lot of community excitement. There are people like Thomas that implements use these GSL capabilities to create extensions for setting systems of differential equations and automatically generating visualizations, animations from these systems of differential equations. And it's great to see work like that. There are also people that realized that by having formal mathematics, you can automatically refactor and generalize your results and propagate them. And in my last minutes, I want to tell you about the Lean FRO, right? This is a new concept that was introduced by Convergent Research. Right? The idea is to have a focused effort, right? They help you raising money for 5-year efforts, right? Where you're going to produce a new piece of code or new equipment or something that will help society. Right? It's something that cannot be done in a corporation, cannot be done in academia because you don't have engineers, a focused team, cannot be done in a startup because they care about being profitable quickly, right? There is no space for this kind of efforts, and FRO is a new model that supports efforts like Lean. The mission is to address the scalability, usability, and proof automation problems I told you about, right? We are going to have 7 employees by the end of the year. We already hired, we have 2 more coming next month, another one coming in November. We are supported by the Simons Foundation, by the Sloan Foundation and Richard Murkin. You can find more about the Lean FRO in our website, lean-fro.org. And I think this quote from Zulip summarizes the challenge really well. The challenge is, can you scale to Mathlib to 2 orders of magnitude? Imagine a world where it's 100 times bigger. There are 100 times more users, right? And there are 100 times more pull requests. Can you do it? I think this is an amazing challenge and something you should aim, right? Should be our North Star. The conclusion is Lean's extensible to improver, right? One, I think if we could pinpoint something why Lean became big is this kind of collaboration model we use, right? It's decentralized. We allow the community to implement their own extensions, right? They don't need to coordinate with us. I believe the Mathlib community will change how mathematics is done and starts, right? And I will pinpoint it's not about proving, but also being able to visualize these complicated objects, right? Getting new insights, communicating, working together, right? Thank you very much for your attention. It was a pleasure to give this talk here.
Thank you so much, Leo. Let's give Leo a round of appreciation. Thank you so much for the very interesting talk about Lean. And now we have time for questions. So the way that we do this is that someone in the chat can raise their hands and you can unmute, and I'll call on you and you can unmute yourself, or you can type your question in the chat and I can ask on behalf of you. So I see that we have one hand in the Topos seminar room. Kevin, you can unmute yourself.
Dana. Okay, I have to come closer there. Can you hear? Yeah, you're probably fine, Dana.
I think if one person speaks at a time, we can hear you quite well.
Anyway, thank you for this inspiring lecture. Very, very encouraging indeed. I have 4 questions, if I may. First, about correctness. I refer back to the FlySpec situation. They had to, in order to get the theorem accepted, they had to prove that the prover was correct. So don't you feel that there's some need now and then for proving things correct in that sense?
Yes, you're talking about programs, correct?
Say again?
You are asking about proving programs correct?
Well, no, proving that the prover itself is proving things correctly. That was necessary for the Kepler conjecture because using a theorem prover wasn't accepted initially, so they had to develop HOL length in order to show that it was provably correct.
Well, okay, it's a great question. Thank you. I can comment. I mean, this is a common, goes back to that slide I had on should I trust Lean, right? I think a powerful way to address at least how we're approaching this question in the Lean community is by supporting different external checkers, right? We can, every proof you construct with Lean every definition, this can all be exported and checked by an independent proof checker. And by having multiple ones is how we increase trust. Of course, some of them you can try to prove, have a verified checker. But in my opinion, having multiple checkers is even more powerful than having a single verified checker. Why? The problem with a verified checker, you're going to have a spec of the hardware, right? You're going to have, there's so many dependencies. By having multiple checkers, I believe, is a really stronger guarantee. Some of them can be verified. That's great, right? But the fact that you have these small checkers that can be independently inspected by humans, but also maybe verified, I think is the way to go. That's how we increase trust.
Thank you. That's very encouraging. Here's a second question of a different kind. Computer algebra, maybe computer algebra is just a chapter under tactics, but so often you want to just say, oh, put the thing into normal form, or invert that matrix, or give me the solutions to that equation. You don't want to prove it, you just want to call up something. So what about incorporating sort of standards kind of computer algebra into Lean?
Yes, this is an ambition we have. And it's a great question because it also points, we had many attempts of combining computer algebra systems with proof assistance in the past. The main problem here is, again, to go back to the funding issue, right? Even after some people connected Isabel with computer algebra systems, PVS with computer algebra systems. But the problem is that these efforts, they rot. This connection must be convenient to use and has to be maintained over time. This is like a piece of software. Even if you solve the problems, the technical problems to make the connection happen, you have to maintain it. In this way, I think this is going to happen for Lean. We are talking to many different people. I had a meeting last year with Wolfram. I mean, he wants to connect Mathematica to Lean, right? And now that Lean is a nonprofit, it's even easier for us to make this kind of connection happen, right? I think this is very promising. There are initial efforts. Rob Lewis is a colleague of mine, a member of the Lean community. He was a consultant at Wolfram Research, and we had a bridge that you could call, for example, Mathematica and ask Mathematica to factor a polynomial, right? And then you could check in Lean if the factorization is correct or not. The hard steps to compute the factorization, but checking is easy. It will start like that. Another possibility is for pieces that are not easy to certify they are correct, we can start by saying we trust the computer algebra system here. At least we are making explicit to everybody that this is a trusted assumption, something that was computed by this computer algebra system. But I fully agree with you, this is a really promising area. There are lots of people talking about that. This person that's Thomas, that was working on the visualization of differential equations, he's big on this area. He really wants to see this happening, computer algebra, scientific computing for Lean. Right? There are many people. William Stein from Sage also, you can find many messages from him on the Zulip channel. He also cares about seeing Sage and Lean talking to each other.
Excellent, excellent. I got a lot of use out of Mathematica and teaching projective geometry, and after getting a formula for a curve, I could call up graphics. And I must say, a picture is worth 1,000 words.
Yes.
Because in the symbols, you can't see where the inflection points are. You can't see maxima and minima. But once you make a picture, then you know what next you need to prove. So combining things with graphics, have you thought about anything along that line?
Yes. These extensions I was showing, the one that showed the graph, creating diagram. I wish I had the pictures here. You can plot graphs. They show how giving a link function, you can ask it, you can write an extension to plot a graph and visualize in the link IDE the graph of the function. Yes, I share with you these enthusiasms about having visualizations. I fully agree. Visualizations help you to understand what's going on, help you to navigate a proof. Yes, I'm super excited about that too.
And my last question, if I may, Martin Escardo and his collaborators have done lots and lots of work in Agda, and he considers much of their work to be new mathematics. And he finds much of the lean library to be old mathematics. Well, of course, I think we've seen many examples of new mathematics coming forth with the liquid tensor project and
Yes.
other things like that. But there is a question about new versus old. Let's take the Kepler conjecture, for example. They had to prove hundreds of inequalities in order to verify that the maximal packing was achieved. But no one is ever going to use those inequalities again.
Yes.
So they're a useless library. But so do we have to worry about old versus new?
No, I don't think we should worry about that. And let's make comments about the first part of your question. I don't like when people start making these comparisons. Oh, this is new, this is old. The Lean Mathematical Library is being developed by high-profile mathematicians. I mean, I'm not a mathematician myself. I cannot claim if what Martin is doing is new, or what Mathlib is old. But I feel like if there's a fields medal level mathematics being done in Lean, by definition, I at least assume this is evidence this is not old, this is new too. And you build, I view also these libraries as gigantic castles, right? You keep building layer after layer, right? And you keep constructing these abstractions on top of each other. And for sure, what you are going to build are going to have very old concepts like natural numbers are going to be on the base, right? But they have to be there. You don't want them to be trusted. You want a justification for them, a definition for these concepts.
All right, thank you, Leo. So we have quite a few more questions in the audience, and I'm going to, in the interest of time, I'm going to ask that each person ask one question. So Valeria, you're next. You can unmute yourself.
Hi, Leo. That was great. A wonderful explanation of all the possibilities and all the good successes already. As you know, we've had in the Topos Colloquium several talks already about Lean, kind of from some of the users' perspectives. So Jeremy talked about it, Kevin Buzzer talked about it, Johan Kommelin talked about it. So we've seen some of the more recent stuff like the Tensor Liquid experiment, and we've seen some attempts also at building up the, say, undergraduate math degree and stuff. So my worry, and it's just a perhaps unfounded worry, is the business of how the Mathlib is going to be organized in the long run. Because, at the moment, as you're saying, you're kind of being able to scale up the engineering of this stuff, but the organization needs to be kind of very clever too, so that we don't in one branch of the Mathlib do things, say, using dedicated numbers, and in the other one use something that we haven't, some other kind of number system that has not been proved equivalent. So I wonder if you have any thoughts already about this business of organization in the long run.
Yes, great question. The first one, the Mathlib community, they were very clear they want is a monolithic library to avoid exactly this problem, right? They want to have one definition of ring, one definition of real number, one definition. Everything is consistent, right? And being monolithic was a big deal, right? Although it was funny because the computer scientists hate this monolithic approach, right? For example, Rust is super popular today. It goes completely against. They have many tiny libraries instead of a big monolithic one. But part of the success of Mathlib is due to the fact they use a monolithic library. Now regarding what are my thoughts going forward, right? I feel like they have to organize themselves. But one thing I want to provide, the Lean as a whole wants to provide, are the tools they need if they want to break Mathlib, or maybe they keep a core of Mathlib monolithic. In many different areas, advanced areas of mathematics, they keep in separate libraries. We want to provide the tools that will enable them to do that, right? What are the tools in this case? It's a powerful package manager. Rust can, for example, Rust can pull these off because they built cargo. I mean, if you haven't used Rust, the experience is amazing. Cargo is an amazing piece of code, right? I believe, I hope that I don't upset them, but I think part of the success is cargo. It works really well. In the Lean as a whole, we are building the equivalent we call reservoir. It's lake is a build system. Reservoir is going to be repository, is going to be the equivalent of crates.io. And we will provide cloud build support for everybody that registered their package there. Feedback, instantaneous feedback, if the packages are not working, are incompatible, right? The developers are going to be notified, look, this package that you depend on have been upgraded. You have a new version and it's incompatible with yours. Maybe you should try to fix that. This kind of tooling, it's key for the mathematical community to be able to explore different forms of organization. Yes. Today, they use the monolithic, works great for them, but also they did not have a good option, right? We didn't have a good package manager for Lean. If they had broken Mathlib into pieces, it would be a mess, everything incompatible with each other, right? The monolithic approach helped them, made them succeed, but moving forward, we want to give the tools they need to try different architectures, different organizational structures.
Wonderful. Yeah. Thank you. Thank you so much for thoughts for the future.
Thank you, Leo. Thank you, Valeria. So I think I will field 2 more questions, and then after that, I'm going to end the live stream. But as everyone knows, we usually stay on in the Zoom chat for even more questions. I see that there's interest in asking a lot of questions today. So I'm going to field 2 more questions, and then we're going to end the live stream on YouTube. So Paul, I think you're next. You can unmute yourself and ask your question.
Right. Thank you for a great talk, Leonardo. Early on, you said mathematicians were engineers, which is very much my opinion, but not one I've heard elsewhere. It's a shame that you said Fields Medal so often. It's rather like saying that the purpose of mechanical engineering is to win Formula One races. I'm a categorist, interested in foundations, interested in mathematical arguments. So it's like looking at the racing car from underneath, or looking at the process of building a racing car from the point of view of nuts and bolts and batteries and motors and all the rest of it. In category theory, we can take an argument from one subject, and by fully understanding it abstractly, we can reapply it in other subjects. So what I would like to be able to do is somehow search the mathematical literature, search Mathlib for where certain kinds of arguments are used across the corpus of mathematics, so that I can say, well, actually, here's a better way of doing what you're doing in a subject about which I know nothing at all. It might be differential geometry, or it might be number theory, or whatever. I ask this question to whenever I attend talks about theorem provers, and other people have not been able to answer that, but I have a hunch that you might be able to answer it.
Cool, great question. Let me just make a quick clarification. I didn't say mathematicians are engineers. I said some of them in the Lean community are great engineers. I view Johan Commelin as an amazing engineer. He managed to organize these efforts, and he creates abstraction layers. He operated as a great computer scientist, software engineer. I didn't try to imply that all mathematicians are engineers. I'm sorry if it was not clear.
What I was trying to say is that mathematics is I like to think of it as being a huge machine in which all mathematicians are engineers,
great.
fiddling with parts of this machine.
Great.
But unfortunately, most of them don't think of themselves in this way.
Yes, exactly. Now to your question, right? The cool thing that Lean is implemented in Lean, and you can introspect. I interpreted your question as, can we introspect? Can you ask questions about Lean as data, the formalizations implemented in Lean as data? Yes, we can. You are going to love this tool. I mean, last week, Johan Breitner, he's an amazing guy. He implemented something called Lugo. Lugo is like based on Hugo. Hugo is a tool for searching Haskell, the Haskell library. You give the type signatures of things, and you can ask, oh, give me all terms that mention these two symbols. There are many. There is a website now, lugo.leanfro.org. You can go to Zulip and search on. You don't even need. It's such a whole Mathlib. And the Lean mathematical library for category theory, it's very rich. I think there's also a cute story. I think I can tell the cute story in 2 minutes. Scott Morrison started, he works for the Lean FRO now. He started the category theory library for Lean many years ago. For many years, nobody saw the point of this category theory library, right? Some people were even saying, oh, why don't you move this to another repository? Nothing depends on this stuff. Why do we need this stuff? But many years later, he kept doing it, right? And many years later, what was needed to complete liquid tensor experiments? The category theory library, right? I mean, it's amazing because he insisted it was important. Many years later, it paid off, right? I love this story, right? And it's great to have Scott with us in the Lean FRO.
Right, thank you, Leo. Thank you, Paul. So we'll have one last question before we end the live stream. Saul, you can unmute yourself and ask a question.
Hi, thank you so much for the talk. It was great. I had a question about not Lean for mathematics, but I'm curious if you know of folks using Lean for building compilers or program optimizers, like in particular, not just verified compilation, but sort of using the same formalisms that you use in proofs, but say to lift like a machine learning code into a mathematical form, do some rewriting based on equivalencies, and then compile to some other language. And I'm curious, if you know of anyone using it for that kind of that work.
Yeah, great question. Yes, this is one area where we want to have more users in the future. We keep learning about applications because Mathlib is so big now. It gets a lot of the attention of the Lean developers, right? But to my surprise, I found recently, for example, Oracle has used Lean. Emina Torlak, that's a colleague of mine now at AWS, but before she joined AWS, she worked on BPF. I'm sorry, I'm not a Linux person, the internals, but BPF is some Linux internal thing they have there, and she verifies this stuff using Lean. Of course, now Lean is implemented in Lean. We have the Lean code generator is implemented in Lean, right? There are people adding LLVM as a backend for Lean to enable people. One of the dreams they have is to give the formal semantics of LLVM in Lean and use Lean as a platform where you can design, compile, implement compilers and prove them correct, right? Going to direct to LLVM. If you have the semantics of LLVM, this is possible, right?
Thank you.
Thank you, Leo. Thank you, Saul. So we're coming to the end of our live stream. I see two comments in the YouTube channel, and I really want to highlight that here. And one, both of them by Kevin Buzzard. So Kevin said I had a student this summer who created a link between Lean and GeoGebra this summer, who could hence visualize an IMO geometry problem that had been formalized in Lean. So I think this is in fact Dana's question about visualizations in Lean.
Yes.
And also Kevin's also talked about the category theory, connection between category theory and the Lean libraries. So he said for several years there was zero connection between category theory and everything else in the library. But when we started developing algebraic geometry seriously, then category theory became essential. Now all of the homological algebra we have in Lean relies on Scott's category theory, and the liquid tensor experiments rely heavily on it. So I think that's really encouraging to hear. At Topos, we do a lot of category theory, and it's good to know that this is a very important part of Lean and mathematics. And Leo, I have one last question for you. Is a quick question. So someone was asking in the chat. I think this is useful for everyone on YouTube channel. Do you have pointers to writings about using GPT with Lean? You mentioned
yes. Zulip is the best way. If you go to Zulip, this Zulip chat for Lean, they have there's a stream called Machine Learning for Lean. They have links for everything there. Lean Dojo, people using GPT, using. They have. I mean, I'm blown away. Sometimes there are huge messages explaining what's going on, analyzing papers, giving feedback about papers that have been published. It's really great resource.
So that's great to know. So go to Zulip channel. Chat channel.
There's a machine learning. I can let me copy the link here.
Okay, thank you.
Yeah.
I think I will maybe put some of these links on YouTube as well. So
yes. Here's the link.
Thank you so much.
There's another question about the search. I'm going to put the link to the Lugo tool. There's also a link to let's see, Lugo slides. You don't even need to install Lean for this one. You can from Zulip you can search. They added an extension to Zulip that from Zulip you can access this Lugo tool.
I see. Very nice. Okay. I think I'm now going to end the live stream for YouTube, and of course, everyone on Zoom is welcome to stay on and ask more questions. So thank you so much, Leonardo. Thank you for your wonderful talk and for answering all our questions. Thank you.
Thank you.
Okay, I'm going to end the live stream now. Okay.